Welcome everyone, I'm Attila and I will present our paper titled Real-Time Sponge and Fluid Simulation. In this presentation, I am going to talk about how we simulate the interaction of fluids and deformable porous objects in real time. One component we need is fluid simulation. The sponge itself is a soft body, and rigid body mechanics are required to model containers or other solid objects. Our work is about finding the coupling points between any two of these simulation systems and providing efficient mechanics for mediating effects one system has on another. Rendering simulated state, still fitting in real-time limits, is challenging in itself, where we also address compositing the fluid, solid and sponge surfaces. First, here are a couple of previous studies I would like to reference before going into the details of our system. Reynolds and his colleagues analyzed the physical laws governing the interaction of fluids and porous materials. Realistic results can be obtained using this method, but it requires offline computing. According to Fay and his colleagues, real-time performance is achieved by constraining flow simulation in the porous medium to 2 dimensions, which is an effective method to simulate wet fabrics, rather than 3-dimensional wet porous objects. Furthermore, both of the methods use different representation of the fluid inside and outside the medium. Our method avoids the need to transfer simulated state between them by keeping a Lagrangian representation in both domains. Real-time interaction also simulated in a recent study by Hung and his colleagues. The point of his work is to avoid the interpenetration of fluids into the material, making the method more suitable for waterproof cloth than porous fabrics. Aborumen and his colleagues combine incompressible SPH and PBD to achieve a two-way coupling. In the 3D case, they use strain-based dynamics just like we do in our approach. However, porous bodies and interpenetration of fluid and elastic material are not considered. Now let's move on to the details. SPH uses radial basis functions or kernels to first compute mass density and pressure near particles, and then evaluate forces. Forces affect the velocities and thus the positions of the particles. In entertainment context, fluid simulation is often required to adopt artistic or fantastic constraints, while maintaining plausible physical behavior. This is possible to achieve using control particles. Recent example is the work of Zhang and his colleagues. We augmented our classic SPH fluid simulation with control nodes. These control nodes introduce external forces. In general, these could be some non-physical effects to achieve some desired shape, like in the image on the slide. In our case, we use control nodes to mediate forces from the porous medium. By using a single detail level scheme described by Wichenbach and Kolb, we reduce the number of particles accessed for evaluating smooth quantities. It's the 2 sortings which we perform with the GPU radix sort that take up most of the computational effort in building this data structure in every frame. Both radix sort and the creation of the cell list and the hash lookup rely heavily on computing prefix sums. We broke the particles array into 30 to 32 pages and utilized the shared GPU memory and waving strings to efficiently compute these. The effect of rigid bodies on fluid are formulated as repelling forces. Considering PBD simulation, first Euler integration is performed in order to find the target PBD positions. Then the PBD solver applies both structural constraints and boundary constraints iteratively. In usual, PBD constraints must be applied sequentially. I will talk about how parallel execution can be achieved in a few minutes. Final positions are used to update velocity. Friction-like forces are typically incorporated into the PBD schemes using velocity filters, altering the velocity before they are applied to the positions again. Position-based methods of solid body simulation replace forces with positional constraints. PBD solves the system by iteratively moving the nodes to satisfy individual constraints. Strain-based dynamics introduces new constraints for triangular and tetrahedral elements, allowing for a PBD-sized solution of a finite element system, offering robust recovery from strong deformations. For our sponge simulation, we adapt these tetrahedral constraints. As I mentioned previously, in theory, PBD constraints should be applied sequentially, but for real-time operation, we decided to adopt the tetrahedral constraints from strain-based dynamics. Parallel execution becomes possible if the elements are sorted in the geometrically disjunct sets with no 2 tetrahedron from the same set sharing a vertex. We achieve this with the tetragonal DISPHENOID honeycomb. The vertices are aligned on a body center cubic grid which easily converted into 2 3D arrays of GPU representation. Each vertex has 24 connecting elements, and 12 of these elements make up a shape that ties the space when aligned on a cubic grid. This defines 12 classes of tetrahedral elements. If we further split them into even and odd elements in a 3D checkboard pattern, we obtain 24 geometrically disjunct classes. Parallel GPU constraint resolution can be executed on all constraints in 24 passes without conflicts. Because of the identical shape of the original undistorted elements, the coefficient matrix for deformation gradient computation is a global constant that applies in every class when adjusted for orientation by swizzling and inverting axes appropriately. This reduces memory requirements and saves significant computation bandwidth. Sponge on fluid effects include capillary section and drag. Section is derived from pore pressure. Drag is a velocity-dependent force that represents the medium dissipating kinetic energy from the fluid as defined by its permeability. We assume the sponge structure is isotropic, so the section tensor reduces into a scalar. This is equivalent to having a constant negative pressure term modulated only by the fluid saturation. This maps well to our controllable SPH method if we consider PBD nodes as control nodes in the SPH simulation. Illustrating this coupling, let me show you a test scenario. I will do so for later coupling as well. This one shows the ability of the porous medium to pull in liquid due to pore pressure. This video shows the fluid visualized with surface normals and the sponge standing in the fluid. Fluid particles and sponge nodes, in other words control nodes, also can be seen in the video. The sponge starts to absorb fluid particles. How high the water rises depends on the strength of the porosity of the material. Drag not only slows down the fluid motion in the porous medium, but if the sponge is moving, it allows to induce motion in the fluid. Thus the relative velocity difference of fluid and medium should be considered. Relative velocity-based force term, viscosity, is already part of the SPH simulation. By computing a similar force over velocities of control nodes, replacing viscosity by the inverse of permeability, we apply a linearized drag model for the porous medium. In the next test scenario, a ball is falling on a saturated sponge. This tests how fluid is pushed out from the sponge as its volume decreases. Material with lower permeability resists this effect more, slowing down the ejection of the water. Fluid on sponge forces are opposing the sponge on fluid ones, moving the sponge itself. Drag is a friction-like force which is typically incorporated into PBD schemes using velocity filters, altering velocities before they are applied to positions. This computation is similar to the evaluation of the viscosity force in SPH, operating over fluid particles. Fluid dragging sponge is a dam break scenario where the drag force acting on the sponge is tested. Given the suction force drawing the fluid into the sponge, and then the velocity filter transferring fluid speed to the porous solid, the sponge will start move away from the fluid. Thus maintaining plausibility, the suction force acting on the sponge cannot be neglected. In PBD, this has to be formulated in the terms of constraints. A zero distance constraint between PBD nodes and neighboring fluid particles is used, with stiffness empirically tuned to balance the suction factor. Looking at this video again, please notice that as fluid is sucked in, moving upwards, the velocity filter would cause the sponge to lift. The constraints counteracting the drag force help us avoid this. Rigid bodies on fluid effects are formulated as repelling forces. Rigid bodies on sponge effects are contact constraints. Both sponge and fluid on rigid bodies are resolved using PBD, adjusting rigid body pose to match constraints against fluid particles and solid nodes. Here, the invisible planes move with constant velocity and are not pushed back by the fluid or the sponge. Also, after the invisible planes effect turned off, the sponge recovers its original shape. Real-time rendering of fluid is challenging in itself, because reconstruction of the surface from a particle representation is expensive, and transparent fluid require tracing reflections and refractions. First, a triangle mesh rasterization is used to display rigid bodies and the sponge. For this, a triangular mesh is generated using the outer PBD nodes. In general, the triangle mesh would not have to match the underlying DISPHENOID honeycomb, and it would be possible to use arbitrarily shaped meshes, disabling the nodes of the honeycomb outside of the shape during physical simulation. We also implemented recursive ray tracing. The surface is found by ray marching. Evaluating density at marching points using the proximity surge acceleration structure, a color and depth buffer laid down by the rasterization. At each marching point, its depth is compared against the solid depth. When the solid surface is hit, its color from the color buffer is retrieved. Based on our measurements, the method works in real time for lower particle and node counts, with acceptable visual quality. Higher particle counts are still interactive. Using around 8,000 fluid particle and 1,000 sponge nodes, the simulation and realistic rendering took around 30 milliseconds per frame. We formulated our control nodes for SPH simulation, but using position-based fluids would likely improve fluid incompressibility and performance. We have not demonstrated simulating multiple arbitrary shaped sponges or larger scale flow. Handling collisions between soft bodies in real time will be extremely challenging. Thank you for your attention.